here. So it says find the ratio of speeds of an electron and a negative hydrogen ion. So it has an extra electron. So we have one electron and then we have two electrons, right? We have an electron and then a negative hydrogen ion, which has two electrons. And they're accelerated through the same voltage. I just want to know the ratio of their speeds. Well, their kinetic energy is 1/2 mv squared, and that's going to be equal to the charge of the electrons times the change in potential. And we want to know the ratios of their speeds. So I'm just going to do, this is V1, 1/2 mv2 squared. We'll make this Q1, Q2, delta V. They both go across the same voltage. Sorry, I know, I'll read the question to you. It says, find the ratio of speeds of an electron or negative hydrogen ion accelerated through the same voltage, assuming non-relativistic final speeds. Take the mass of the hydrogen ion to be 1.67 times 10 minus 27. That's a proton. So if you do this, if you set this up, setting the kinetic energy equal to this work term, Q delta V. Now this idea is something that is certainly important for the exam. This particular problem, maybe not, but probably not. The masses here are the same, because when you add an electron to a proton, it doesn't really change the mass of it that much. So if I just take the ratios of these, I can cancel these out, cancel that out, and that should give me the right answer. Actually, let's see, so I need to cancel those, excuse me, not that. Cancel these, square root both sides, I get V1 over V2 equals the square root of Q1 over Q2. Should be something along those lines. Yeah, the mass is not important. I mean, because the mass of each of them is the same. Sorry, I went dead. Oh, there we go. Yeah, the mass of both of the electron and the negative hydrogen. Oh, wait, no. The masses are different, actually. So, yeah, you do have to consider the masses. Because you have enough.
Twice the mass of the hydrogen?
No, the hydrogen has a proton. So you have to include the mass of the proton. All right? Probably. If you're not including the mass of the proton, you can think of the hydrogen just as a proton, actually. And that should get you to, that'll get you to the right answer, because they're all very different.
Yeah, because that's what I took it as, that the given mass for the hydrogen ion is the total mass. And you just use the one electron of the...
Well, this is the mass of the hydrogen ion. The mass of the electron is just the mass, 9.11. Should be enough.
That's fine.
All right. Are there any other questions about the quiz that's due tonight or tomorrow night? No. If you do, feel free to drop by me tonight. But for the one due tomorrow, if you have questions, I'm willing to help you along in my office if you have questions about them. All right. Let me just sort of give a quick little summary of what the exam is going to cover. It is covering Chapter 1 and part of Chapter 2, what I'm calling 2A, right up until capacitors. You will not see any capacitors at all, not even a little bit. So I know in the in-class section we've covered a little bit of capacitors, and we'll continue probably for about 10 minutes tomorrow covering a little bit of capacitors, but you won't see any on the exam. All right, so as you're going through the old test, if you see questions with capacitors, just skip over that. Now, we're doing forces, fields, and potential. So we have forces, fields, potential, and then we also have potential energy, which I sort of grouped together with potential. So with forces, you need to know how to do those qualitative things, like we did some in class, like you had this collection of charges. Show me the vector that represents the coulombic force, the electric force, the electrostatic force. Also be able to calculate the electrostatic force. If I have a plus and a minus charge and I give you the charges and the distance, make sure that you can determine what is the force on each of those. both quantitatively and qualitatively, being able to calculate those forces. Similarly with fields, be able to calculate a field in 1 and 2D. All right. Being able to find the magnitude, you will have to use, of course, the Pythagorean theorem and all that business to find the magnitude of these, either the electric fields or the electric forces, because you will have 2D vectors. You should be able to do this qualitatively as well. You can't read that? Calculate the electric field in 1 and 2 dimensions. So you might have one like this, and I ask you to determine, say, the electric field at a point in between them. Or I might just give you one charge and say, what is the electric field over at this point? Right? Or you could have electric field of, say, 2 charges like this and the electric field at that point. Those are slightly different problems. Be able to determine the direction of the electric field qualitatively, and then also be able to determine the force due to an electric field. That's that whole F equals QE bit. Be able to draw field lines and equipotential lines. So field lines and equipotential lines. Know how those are related. Equipotential lines are perpendicular to field lines, and know what they represent. Equipotential lines represent lines on which the energy doesn't change. The potential or the potential energy of a charge does not change. Similarly, be able to calculate the potential. Know what potential is, by the way. On all of these, you should know what they are. A field is a force per charge. A potential is energy per charge. And then potential energy is just energy. Be able to calculate potential for a point charge. Or one or more point charges. That's this V equals KQ over R. We've done several of those in class or in your online bit, calculating the potential of a collection of charges. Right? Also be able to do that qualitatively. Look at a collection of charges and tell me where is the potential equal to 0, like we've done in some of the online bit. We'll look at some of the old tests for that. Potential, what else on potential? I think that's it. We'll try to keep that in mind as we go along. Now for potential energy, be able to calculate the potential energy for a collection of charges. That was the, like if I have 3 charges here, I calculate U for 2 charges, for another set of 2 charges, and then also for the third set of 2 charges, calculating U for all of those, and then adding them up. That tells me the total potential energy for those 3 charges. We did this in the homework, or you can see it in the old test. We'll look at one in some of the old exams as we go along. All right. There is one other thing you need to know, and this came up particularly in the OpenStax bit, the tutor. Know the relationship between the fields and the potential. If you think about the fields, the field, say if I have a field of 1 Newton per Coulomb, that's also given in volts per meter. And so these units imply that there is a relationship between the potential and the electric field and the distance over which something travels. So for example, or actually on your equation sheet, I think it's on there, let's double check. Yeah, here it is, that our potential is related to our electric field. V is equal to EX. There's a negative in there, but we're just sort of thinking about the magnitude. So our potential is related to our electric field based on the distance that the object travels. So if an object travels through an electric field over this distance, then it's covered that change in potential. We have some questions from the OpenStax quiz that's due on Friday related to this, and some of your reading was related to that as well. All right? Any questions just sort of about the general overview? All right, let's look at some old test questions, okay? Are there any particular questions about old tests, or do you want me to go through them and sort of, you can holler out when you see things? Or any particular questions now? No, that's okay. We'll address them as we come up to them. Let's start with, we'll look at spring 16, as last year. All right, so you will need to know some just sort of basics about charge, about the quantization of charge, about how it's conserved, and then also how it makes up certain things. We had several questions on the reading in the quiz that was due, or that is due tonight, about the properties of charge. So, you know, like for example, this question is about the up quark, which has a charge of plus 2/3, and a down quark, which is minus 1/3 Z. Those are sort of partitions of the electron or the proton. What combination of them makes a neutron, which has no charge at all? And so we just want to know what combination of these charges, plus 2/3 and then 2 minus 1/3, would give us a zero charge. So that would be up, down, down, would be UVD. D is the answer. But similarly, we had similar questions about charges, how charges add up, and then also how charge is quantized based on the fundamental unit of charge. Basic ideas about they're attractive or repulsive depending upon the nature of the charge. I think we're probably okay, but you're going to see 5 or so questions based on that. Have any questions about these in particular? Okay, it's not really, it is sort of, that part is new, but really the important part is that these charges add up to give us zero charge. Let's just sort of step through it since it is sort of new. So these atomic particles, neutrons, protons, electrons, they're made up of these subatomic particles called quarks, and these quarks have particular charge. So like the up quark has a charge equal to plus 2/3 of the fundamental unit of charge. And the down quark has a charge equal to minus 1/3 of the fundamental unit of charge. And we want to know what is a neutron then made up of. The only combination of these that will give us zero charge, which is a neutron, is 1 up quark and 2 down quarks. Because 2 minus 1/3, or excuse me, 2/3 minus 1/3 minus 1/3 is equal to 0. And so similarly, like an electron would be, what would an electron be made up of? Well, 3 down quarks, right? Minus 1/3, minus 1/3, minus 1/3 would be minus 1. A proton, on the other hand, would be 2 up quarks and a down quark. 2/3 plus 2/3 is 4/3. Minus 1/3 would be 1 fundamental unit of charge. Okay? Need to know how to do this, or we have force vectors or electric field vectors. It could be a different configuration. You're going to have forces in 1 and 2 dimensions, so make sure that you can do those. This looked difficult, but it was really just sort of a one-dimensional problem. You're going to have problems where I ask you what happens when you change the distance, or what happens when you change the charge. With that, you need to remember your equations, and these are on your equation sheet, but you know, just be aware of them. Those equations are F equals KQQ over R squared, E is equal to KQ over R squared, Z is equal to KQ over R, and then U is KQQ over R. These are vector quantities. These are both scalar quantities. And just to sort of remind you about this, that whenever you're calculating these two, don't use any signs. So if I have negative charges, don't include them in your calculation because the signs come into play when you actually figure out what are the direction of the vectors when you're drawing those vectors. However, for these, if you have negatives, you need to include the negatives. Sometimes with potential energy, we wouldn't do that. We would just sort of give the magnitude of the potential energy, but typically you're going to include your negative. You would know this if you didn't include this because there wouldn't be any negative answers. Okay? So those are sort of our big governing principles, and you need to sort of, those are on your equation sheet, but it'd be nice for you to just know those right off the top of your head. Okay, field lines, you need to know how to do that. Anything stand out to y'all on this page? Yeah. Okay, so you're probably going to have one like this, frankly. It'll be different numbers, but it'll be something very similar. In fact, I'm pretty sure that it's an electric field problem like this one. It doesn't really matter if it's an electric field or a forces problem. You work them out very similarly. I'm pretty sure I gave you an electric field problem. So I want to know the electric field at point A. So I'll start there. The first thing I want to do is draw the vectors due to each charge. So the electric field due to that charge is in this direction. I know that because I imagine a positive test particle there and ask myself, what is the direction of the force? The direction of the force is towards that negative particle. Due to this particle, the electric field is in this direction. So those are my two electric fields. I know that in the end, my net electric field is going to be in that fourth quadrant. It'll be in the fourth quadrant because those two vectors, you know, if I combine them, they put that vector in the fourth quadrant. So my first step is just to figure out what is the magnitude of the 2 nanocoulomb charge. It's going to be K. Q. Don't forget your nano is -9 divided by R squared. That's 3 squared. So the 3 squared and the 9 cancels. That cancels with that. And we're just left with 2 newtons per coulomb. That's in the negative y direction. And then doing E due to the -1 coulomb, I get 9 times 10 to the 9th. 1 times 10 to the -9 divided by the distance squared. That's 3 squared. Well, this cancels with that with that, and I'm just left with 1 newton per coulomb. I try to give you as easy number as possible. It's not always easy numbers, but I try to make that part pretty quick by giving you easier numbers. So I know this is 1. I know this has a magnitude of 2. And so to figure out the resultant, I say the square root of 1 squared plus 2 squared, square root of 5, which is what? 2.2. All right. You also want to know the direction. You'll have to do both of these on the test because I want you to make sure you got vectors before we move on. To find the direction, I want to know this angle theta. I do theta is the inverse tan. Gosh, was it opposite over adjacent or adjacent over opposite? It's right, so it's y over x. So the y component is 2 over 1. I don't know what that is. Y'all are pretty much been doing this for a while, so I think y'all are probably okay on this. I get 63 degrees. That's 63 degrees below the positive x-axis in this case. Always good to draw your picture so you know which quadrant it lies in, so you can define where the angle is. So that was number 12, 63 below the positive x-axis. Okay, you will have one of those. We've done those a bunch this semester and last semester, but you know, several questions on that particular topic.
I don't really know how to go about working out.
Okay, you're gonna have one of those too, right? Just this idea of, is there a point where the electric field is equal to 0? Or we could ask a similar question about the forces. But looking at this, where is the electric field equal to 0? I just sort of start with the points and ask myself, what are the directions of the electric fields at these particular points? So let's consider point E first. We'll say this one's blue and this one's red. Due to the red charge at point E, the electric field is in this direction. Due to the 2Q charge, it's in that direction. I drew it smaller because the charge is smaller and I'm farther away. But look, those two vectors on the right-hand side will never go to 0 because they're always going to be both pointing to the right. They'll always add up to something. Let's try in the middle now. Due to the plus 2q, say it's C. Actually, the answer is going to be B, so I'll start here. It's going to be in that direction, and due to the plus 4q charge, it'll be in that direction. Turns out that B is the answer, so we need to distinguish between B, C, and D. Now, if I'm at D, let me draw the vectors for D. For D, the vector due to the plus 4q charge is going to be really big, and the plus 2q charge is going to be smaller. The reason is, and it's similarly for C, the reason is I'm really close to this big charge, and I'm further away from the small charge. So I get a big vector due to this this plus 4q, and a smaller vector due to this. These two vectors are never going to cancel out. But over here, when I'm further away from the big charge and closer to the small charge, then it's possible for those to cancel out. Okay?
If they're both, like, let's say a positive 2q charge, would C be where?
That's a good, yes. Yeah, a good question. So if they were both plus 2q, C would be the answer. All right? Those plus and minus. What if it was a plus and a minus? Say, what if it was a plus q minus q? Where would it be 0? Is it ever 0? Yeah, it must be. Here. Here. No, it must never be 0 if we have a plus q minus q. Because you're always, like, if I think about over here, due to the plus q, the field is in this direction. Due to the minus q, it's in that direction. It's always going to be smaller. And in a similar way over here, due to the minus q, the field is big and in that direction. Due to the plus q, it's small and in that direction. So if I have an equal plus q minus q, never a place where the electric field is equal to 0, at least along that line. With these, though, you just need to go through and ask yourself, what is the direction and what is the relative magnitude of the vector? And that's related to Q and it's related to R, because E is KQ over R squared. Listen, there are lots of these questions in the old exams, and you'll see a couple, I'm pretty sure, I think they had a couple that were similar to these that sort of explore that idea. Not just electric fields, but charges, or forces as well. Does that help a little bit? Yeah, if you haven't mastered it, you need to master it. I'm around tomorrow, I can help too. So. All right. Can I clear all this? All right. Need to be able to do some basic kinematics. We had that kind of stuff in homework. If you see anything with capacitors, it's not going to be on the test. And it might even be sort of interspersed with some of the potential problems. So if you get to capacitors, look past that and see if there are any other potential problems. Stuff like this, where is the potential equal to 0? We had several of these in the clicker questions or the OP quizzes. Well, where would it be for this one? Where would the potential be equal to 0? You want to look for a place where you're equidistant from opposite charges. So like, for example, here, I'm equidistant from these two charges, so the potentials cancel out. Similarly, equidistant here at that point. But it turns out actually that here, here, and here all have a potential equal to 0. Because I'm equidistant from the positive and negative charges. See here, these two charges are the same distance away, so their potential cancels out. These two charges are the same distance away, so their potential cancels out. These two charges are the same distance away, so their potential cancels out. It's E on this one, yes. All right, but if you have a different configuration of charges, it could be A, B, C, or D. It just depends how you move the charges around. look at what is the sign of the charge and how far away are you from the charge. Alright? Of course, you need to know how to find your units. I think that y'all are probably pretty good on that. Need to know about equal potential lines. Yes.
I have a question.
Okay.
That scenario, the electric potential would be the greatest at B, correct?
Right. Because potential is KQ over R. Right? Q here is constant. It's staying the same. R is the only thing that's changing. So if R gets small, V goes up.
What would be a question that you would ask where, like for B and D would be the same, like the answer would be the same? Because on one of the exams.
Okay, good question. So if I'm on an equal potential line, so if I had another E, say there was an E somewhere along here, let's say that E. Oh, actually, no, the answer here is A. Oh, no, it's not. No, it's not. I'm sorry. The answer is B. But let's say that I had another point E. Is it looking for the least? Yes. Okay.
But B is the most.
Shoot, I'm sorry. B is the most. Yes. Because R is small. A and D are the least. A and D are the least because they're on an equal potential line. Does that answer your question?
Well, what I'm wondering is, when will the answer ever be like, it doesn't matter, right? You know what I'm talking
Like, she's saying like if we had another point where on the same line as B.
Mm-hmm. And if I had another point on the same line as B, and I was asking for where is the electric potential the greatest, then it would be B and that E point. Because when you're inside, when you're close, for a positive charge at least, the potential is greater. Listen, in the in-class section we talked about this, like a mountain. I don't know if this helped y'all or not, but if you have a mountain, huh? If you have a mountain, you can think of topographical lines on the mountain. Here I have lots of potential. Here I have not much potential. Because the same idea applies for like gravitational potential energy. As I go up higher in elevation, I get more potential. And so you can think of this as like looking down from the top of the mountain. So this is like the peak of the mountain, and then these are the topographical lines as you go down the mountain, like on a topographical map. So they show lots of potential, not much potential, even less potential. Now be careful. I'm not going to give you the negative charge, but if you saw a negative charge elsewhere, it would be flipped. It would be like a hole in the ground. Because a negative charge has a negative potential. All right. Be able to find the potential due to multiple point charges. It could be 2 or even 3 charges to find the potential due to those charges. It's a lot easier than finding fields because they're not vectors. When you're finding the potential due to point charges, you say V equals the sum of KQ over R. So for example, at this point, if I want to know the potential due to here, I would say that distance is 5 meters, and the potential just due to that 5 nanocoulomb charge would be 9 times 10 to the 9th, 5 times 10 to the minus 9, that's my Q, divided by 5 meters, and that would equal, that cancels, that's equal to 9 volts. Just due to that plus 5, what would be the potential due to this minus 10? What have I done to the distance? Is it the same or different? It's the same. What have I done to the charge? I've negated it, doubled it. So what's the potential going to be here? It's going to be twice this and negative, right? Negative 18. So the total potential will be negative 9. Negative 18 plus 9. All right? So guys, make sure you go through your OpenStacks. Once you get your, yeah, can I clear this? What's up? Make sure you go through your OpenStacks quizzes once you get the solutions to them. Because I did pull 3 or 4 questions that are almost verbatim. I changed the numbers. but almost verbatim. And they're not wonky questions, right? I mean, they're stuff like we did in class, but I pulled them from the OpenStack. So make sure you look back at those too, because I did use some of those questions. Not from your personalized, only from the 5 that I chose, or 5 or 6 that I chose. All right? So I'll just sort of do that just to sweeten the deal with the tutor, so it's worth your while to go back and review those things. I'm sorry, Olivia, you were going to say?
Page 13, could you just clarify what exactly you were finding? We use like cosine and sine, and I think I got one of the ones wrong because I tried to do it and I was supposed to, or I needed to and I didn't. And I don't know when you're supposed to.
This page right here? Okay, what was your question?
Is it supposed to be at that point in the center?
Yeah, right. So at this point in space, there's an electric field. You don't need a charge to be here to be an electric field. Like there's an electric field whether you have a charge here or not. In fact, if you had a charge, it wouldn't even affect the electric field at this point. It would affect the electric field at other points, but not at this point. So the electric field here exists because of this charge and this charge. All right, you with me?
The reason we use cosine sine is because there's no other numbers except for the distance on either side of the
Right here.
yes. Like, is that why you use cosine and sine?
We use cosine and sine because I have this vector that's off in the first quadrant, and I need to find the x and y components of it. So that's all I've done here is I've said E1, which has a value of 1.08 times cosine of 37. That is the x component of this vector.
But in the example we just did, when it was the fourth quadrant, we used cosine and sine. Is it because we had the distance already?
That was potential. This is field. So remember, potential is a scalar quantity. And so I don't have to do that. But if I'm dealing with forces or fields, those are vector quantities. That's a good question because a lot of students are going to sort of get those mixed up in their minds. But remember, forces and fields are vector quantities. And if you don't treat them like vectors, you're not going to get anything even close to the answer. I mean, I guess you might by chance happen across a number, but probably not at all. I don't even consider that you would do that. Okay, but remember, students will make that mistake. So remember that fields are what are they? They're vectors, right? And forces are also vectors, and potential energy are both scalars. Okay. It's a tough test, y'all. Like, this is, in years past, it's not always the case, but in years past, this has been the lowest average of all 4 exams. I don't want to scare you, but I do want to scare you just a little. Okay? But you can do well. You can do well. I mean, it's a lot like these exams that you're seeing. It's different, of course, but a lot similar to them. Okay, what else here? Anything stand out to you folks? Oh yeah, the electric potential units. So electric potential, first of all, potential is energy per charge. Right, that's sort of our basic fundamental idea of what is potential. And so energy per charge, hey, that's energy per charge, right? Because a joule is energy, charge is energy. Potential is also measured in volts, so that's also an appropriate answer. So I know it's either B or E, because I know 1 and 2 are okay. But let's look at 3, energy per charge. Well, let's see, what is energy? Well, I can think of kinetic energy, 1/2 mv squared over Q. And so that would be kilograms meters per second squared 1 over coulombs. Is that the same as this? No, that's not the same. So it's just going to be B is the right answer. So on these, like we've done in the past, you need to think about either the equation or the basic idea and figure out what are the basic SI units. Now, if you wanted to go actually to the potential equation, you could do so too. Like if you forgot this idea, you could say potential is KQ over R. And you know the units for Q are coulombs, and you know the units for R are meters, and you can get the units for K, they're on the equation sheet. So you could take that route too if you wanted. Huh?
Probably wouldn't use that.
No, you wouldn't have.
Probably because
You
of the
wouldn't.
S4 and the S2, I probably would have overlooked it.
That's a
It's
fourth.
sneaky.
That's a fourth power, and this is a
I know,
square.
but I probably would have.
They're so different things.
Sneaky. I know they're different, but
Well, you gotta read them carefully. I mean, that's life,
it's a
right?
good
So,
point.
yeah. All right.
Well, we have one similar, number 26.
Let's just take a look. I don't know if I can tell you right off, but what's 20 what? Yeah. Mm-hmm. So the kinetic energy, we sort of looked at this as sort of the question we were looking at the beginning. You can think about this in a couple different ways. Probably, I give this little hint. What is the potential difference between the two plates? The work, which all goes into kinetic energy, is equal to Q delta V. So my kinetic energy, 1/2. Actually, no, I don't even know that. Yeah, I want to know how much kinetic energy is equal to Q times delta V. So I have a 2 coulomb charge that's moving across a change in potential. It's going from 5 volts to minus 5 volts. So that's a change in potential of 10 volts. So the answer is going to be 20 joules. But yeah, that basic idea of work as Q delta V is certainly, you can certainly see that on the exam. This one is a little bit different because we were talking about, this difference in potential across two plates, but the same idea still holds. Because I start at 5 volts, I go over to 0 volts, and then I go to negative 5 volts. So I do 5 minus negative 5, 10, which is 10 volts. It's like in your house, in your house you get those 220 devices, 220 volt devices, like your clothes dryer and stuff. Are you know what we're talking about? Those operate at 220 volts because you have one wire at positive 110 and one wire at negative 110. You don't actually have 220 volts coming in, but you have a difference in potential between 110 and negative 110.
If we would have had a negative 2 coulomb charge, we would have to add the negative 2 into that formula, into the equation.
No, because kinetic energy is a scalar quantity. It would still get the same amount of energy. And there are no negatives. Well, I wouldn't get any negatives.
Why wouldn't you do for the voltage the negative 5 minus 5? Because it's final minus 3.
Oh, you could do that, but you would just drop the negative.
Okay, it would still give you 10.
Mm-hmm. I was just looking for
Okay.
the negative doesn't really mean. Okay? Is that clear? I forgot who asked that. Was you over there?
Oh, yes, it was this one.
All right. Can I clear this? Let's just sort of peruse this one too and just take a look. Oh, this whole idea that positive charges move from, what do they move from? It's like a ball rolling down a hill. They move from high to low potential. Negative charges, on the other hand, move from low to high potential. So if you think of a positive charge, like think of the mountain, positive charge is going to roll downhill. It'll move from high to low potential. Negative charges just do the opposite. They move from low to high potential. This question, 28, asks the amount of work required to assemble these charges. The amount of work is equal to the potential energy of the charges. So you would consider the potential energy of these two charges. Remember, U is K, Q, Q over R. I think you have one question that has to deal with something along these lines. Yeah, of course. So here I would find the potential energy of that two collection of charges. It's going to be 9 times 10 to the 9th. Can y'all see that? Okay. 3 times 10 to the minus 9. 2 times 10 to the minus 9. Divided by the distance. This distance is 5 meters. It's a 3, 4, 5 triangle. You can use your Pythagorean theorem if you're not certain about that. And so let's see, that cancels, that cancels. We have 18 times 3 is 30, 54, times 10 to the minus 9. I get 1 times 10 to the minus 8. That's in joules. And then similarly, I'll do these two. 9 times 10 to the 9th. 2 times 10 to the minus 9. 1 times 10 to the minus 9. Divided by 3. Notice there's no squares here. There's no signs either. They're all positive actually. These cancel. This cancels with that. I get 6 times 10 to the minus 9. And then I would consider the third configuration of charges to be 9 times 10 to the 9. 3 times 10 to the minus 9. 1 times 10 to the minus 9. Divided by the distance, which is 4. Cancels, cancels. It's 27 over 4. 6.8 times 10 to the minus 9. And then to get the total, I just add all these up. So 1 minus 8. 2.3 times 10 to the minus 8. Must be C. I must have rounded somewhere along the way. But you look at each individual set of charges. Now, if you just have 2 charges, it's easy. You just do this once. If you have 3 charges, you have to do it 3 times because you have 3 distinct pairs of charges, and each of them contain their own potential energy. You won't have more than 3. Yeah.
So if the charge is negative, we have to put a negative.
You're right, Bethany. Yeah, I'm sorry I didn't have one here. But if it was negative, you would include the negative. Because it would introduce a negative potential difference, or negative potential energy, and it would sort of take away from the others. All right? I think one question. I'm not that concerned about this. It doesn't come up again. All right? I have to go in about 5 minutes. I have to pick up my kids off the bus. But yeah, is that okay, ladies? All right, what is it?
The same quiz due Friday. It's question 2.
Do you have it somewhere? Let me see. How am I going to do this? Let me start this back. Bring this back. So this is a question. Now you can find, and this is really what's important for our test, because I wouldn't give you this on the test, but let me get you in the right direction on this. So I think that you can find the amount of energy that the battery, the amount of energy that the battery provides is Q times delta V. You know delta V, it's 12. You're looking for Q. Right? That's the work that the battery does. That's the electrical energy output that it gives you. And now you want to set that equal to the mechanical energy. And the mechanical energy has 3 parts. It's the part that takes the car going from rest to 25 meters per second. That's the kinetic energy. So it's 1/2 mv squared. Then you want to do the part that makes it climb this Hill, that is mgh. Go with me? Remember last semester? And then we also have the final part. We did this a little bit last semester, but I want to have it travel at a constant 25 meters per second for 500 newtons force for an hour. The power is equal to F times V. That's force times distance over time. And so our power is F times V. The work is equal to power times time. So this is going to be the work required to make it do this business is going to be the power, which is F times V, that's 500 newtons, times the speed, which is 25 meters per second, times the time, which is for an hour. Oh, actually, that should be 3,600 seconds because to have it in SI units. Now, those three terms, all added up, are going to give you the total mechanical energy. And all that mechanical energy has to come from that battery for this business to work. We know the mass of the car? Yeah, we do. It's a 750 kilograms, so each of these are 750. And the speed of the car, we're told, is 25 meters per second. You know, G, of course. H is 200 meters. And that's it. Delta V is 12. Try that out on your own. If it doesn't work out right, this is the one due Friday, right? Is that right? One of y'all email me if it doesn't give you an answer, but that should give you the answer. It's a little, that one's a little tricky, wasn't it? Like you had to remember a lot from the previous semester.
And that one's one that's
No. I picked ones that were more akin to what we've seen. Listen, if you ever come across a problem like that, you're just like, I have no idea. Shoot me an email. I'm okay with that. But shoot me an email prior to 7:30 on the night it's due, please, because otherwise I won't answer it. Oh, I gotta go. Is that? I'm sorry. Any other questions, John? All right, we're gonna be okay. We'll have another low review session in class tomorrow. I don't know if y'all can make 4 a.m. Probably not, but I'll post the link on it. I'll be around tomorrow too, so if y'all need help, that's my job. Okay. I have a meeting at 2, but I'm around otherwise.
So, I get off of work for your, it's gonna be after class.
Schedule it.